Welcome to all. In this video we will see the axiomatic definition of Boolean algebra. So in the one of the videos which I uploaded previously, so you have seen what you mean by Boolean algebra and some of the laws involved in Boolean algebra. So in this particular concept we will see some examples of postulates where we use positive and multiplication symbols or dot operators for the solution of the problem. So there are some postulates which you can see on the screen. The first one is the closure with respect to the operator plus. So this is one of the postulate which you have to remember. So these things are required when you go for theorems or to get the solution of the theorems which we are going to see in the next upcoming slides. Okay, so the second postulate is closure with respect to the operator dot. So mainly we are dealing with the plus operator and dot operators based on the problems which we are going to take. The second one is an identity element with respect to positive sign and designated by 0. So it is something like x plus 0 equal to 0 plus x, and ultimately we are going to get the value as x. So that means in this particular instruction you can see the positive symbol. How can you make use of positive symbol, and what will be the result you are going to obtain at the end. And the second option is an identity element with respect to dot operator. How exactly you can visualize it? So it is something like x dot 1 equal to 1 dot x, again it is equal to x. So even though it is a positive symbol, or it may be the operator which you are going to use is dot, ultimately you are going to get the value as x. So the third one is commutative law, or commutative with respect to positive sign. That means x plus y equal to y plus x. So all these laws or postulates are required when you are going to solve the instructions, whatever the instruction we are going to give in the problem. Okay, the second one is commutative with respect to dot operator. So it is something like x dot y equal to y dot x. The fourth one is distributive over positive symbol. So in this particular line or in the sentence you can see both the operators, dot operator as well as positive operator. That is nothing but x dot y plus z can be represented as x dot y plus x dot z. That is nothing but a simple multiplication, isn't it? So you are going to multiply x with y as well as z, and ultimately you are going to get two instructions. That is nothing but you can put the one instruction with respect to with inside the brackets, and another one is with another bracket along with the positive symbol. The second one is plus is distributive over dot operator, or positive symbol positive operator is distributive over dot operator. That is nothing but that is nothing but x plus y dot z can be represented as x plus y dot x plus z. A simple multiplication, but with respect to operator you have to be more careful while solving it. Okay, the fifth one is for every element you can see how exactly the b can be represented, or the elements which available in the x or x dash. So that can be called as complement of x. We can say complement of x when we are going for x bar or x to the power, that dash symbol whenever we put it can be said as complement of x. So you have two instructions, x plus x dash equal to 1. So you have to remember this, and x dot x dash equal to 0. So wherever in the theorems, while solving the theorems, if there any concept of 1, that means 1 can be represented as x plus x dash, isn't it? So you have to remember this particular concept, x plus x dash equal to 1 as well as x dot x dash equal to 0. The sixth postulate is there exist at least two elements when you consider x comma y which belongs to B, such that x is not equal to y. So the x should not be equal to y. So there are some postulates which you have to remember. So these postulates are required to solve the theorems as well as problems. Okay, so that is the reason why I uploaded this. Now you can see the second slide. So comparing Boolean algebra with the arithmetic and ordinary algebra. Okay, so there are some points which you have to remember. So there is a concept of Huntington postulates. So that is one of the postulates which you have to see. We can say it's a kind of law, okay, they say that do not include the associative law. So in the previous video you have seen what is associative law, distributive law, isn't it, commutative law. So you have to remember that laws to solve some problems. Okay, it is better you note down somewhere and you can keep it for the future references. Fine. However, this law holds for Boolean algebra and can be derived from the other postulates. So derivation can be done using other postulates, whatever the postulates you have seen in the previous section. Okay, the second one is the distributive law of plus over dot. So something like so this is the same instruction which you have seen in the previous slide. X plus y dot z equal to x plus y dot x plus z is valid for Boolean algebra, but it is not valid for ordinary algebra. You have to remember this. So there is a difference, or if you want to visualize the difference between ordinary algebra as well as Boolean algebra, you can see the distributive law over plus and dot symbol will not holds good for ordinary algebra. The third one is Boolean algebra does not have additive or multiplicative inverse. Therefore, there are no subtraction and division operations. So in Boolean algebra, you have to remember this additive and multiplicative inverse will not be available. Okay, the fourth one is postulate 5 defines the operator called complement. So in the previous slide, you have seen that dash symbol, isn't it? X to the power dash. On one you are going to put one dash, so it is nothing but complement. Fine, is not available in ordinary algebra. So that complement concept is available only in Boolean algebra. You cannot see that particular thing in ordinary algebra. The fifth point is ordinary algebra deals with the real numbers which constitute an infinite set of elements. Boolean algebra deals with the as at an undefined set of elements b, but in two-valued algebra defines. So there are some concepts which you are going to see in two-valued algebra as well. B defined as a set with only two elements, 0 or 1. So because ultimately when in this particular system, okay, the computer organization, whatever the subject you are going to learn, it is okay, but when you deal with the digital logic or the circuits which you are going to build, at that time the input will be in with respect to zeros and ones, isn't it? Ultimately computer will understand only zeros and ones, or binary system. So that is the reason why all these algebraic concepts are required for the solution. So the next concept is two-valued Boolean algebra. So you can visualize it here. Let me zoom little bit. So I have taken this screenshot from the textbook because I tried to find the soft copy of this particular textbook and I couldn't get. So that is the reason why I just have taken the picture and I uploaded for the explanation. So once the college starts, you can visit a library and you can opt for the book which is required for your subject. Fine. Now you can see the tables. It's something like a truth table, isn't it? So x and y, those two can be the input, and ultimately you are going to get the output if you use the dot operator, plus operator, and complement. Complement is nothing but inverse. So if the input is 0, if you complement the input, then you are going to get 1. So it is something ulta. Okay, if the input is 0, then you are going to get the output as 1, and if the input is 1, you are going to get the output as 0. So it is an inverse operation. The complement is nothing but the inverse operation. So you can see the truth table. So 0 0 is 0, 0 1 is 0, 1 0 is 0, 1 1 is 1. So it is a normal multiplication concept. With respect to plus operator also, it is nothing but or operation, isn't it? And operation, or operation, and not operation, both are the same. So whatever the operations you have seen in the previous video, the same concepts are repeating here, but with respect to Boolean algebra concepts. Okay, these rules are, so that is the reason why in the textbook also they have given these rules are exactly same as and, or, and not operation. Okay, so there is nothing different concept which you are going to learn. It's the same thing, but the terminology may differ from one another. Okay, now here you can see Huntington postulates are valid for the set b equal to 0, 1 and the two binary operations defined above. Okay, so the first one is, so you can see some points they have listed out there. So closure is obvious from the table since the result of each operation is either 1 or 0. Why? So because again when you are going to deal with the binary concepts, again ultimately you are going to get the value as 0 or 1. The second point is, from the table you can see 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1. Ultimately they are trying to prove that how exactly positive symbol and a dot operator works. Okay, so you can see 1 into 1 equal to 1, or 1 dot 1 equal to 1, 1 dot 0 equal to 0 dot 1 equal to 0. That is the same thing what you have seen in the postulates, isn't it? So while I listed out some postulates in the previous slide, the same thing they have tried to represent. Okay, so which established the two identity elements, 0 for plus and 1 for dot. Okay, in the, say, as defined as the postulate. So they have specified over there. The third point is, you can see the third point, the commutative laws are obvious from the symmetry of the binary operator tables. So commutative law also can be tried to prove, you can try to prove using zeros and ones. The fourth one is the distributive law. So x dot y plus z equal to x dot y plus x dot z. So distributive law, how exactly the distributive law works, based on that they have tried to build the table. You can see the table x, y, z when you have three inputs, x input, y input and z input. So when and three inputs are 0, then y plus z is 0, x dot y plus z is 0, x dot y is 0, x dot z is 0, x dot y plus x dot z also 0. So you can try to replace, okay, so when x is 0, y is 0, z 0, based on that particular table, you can see you can replace y with 0 and you can replace z with 0. Again you are going to get the output as 0. You can, in the second table, you can see x dot y plus z. Again x can be 0, y can be 0, z can be 0. Ultimately you are going to get the value as 0. So you can try to replace the values with respect to the given values or input values. Okay, the fifth point is, so before that, in the fourth B, you can see the distributive law of plus over dot can be shown to hold true by means of the truth table similar to the one above. So these truth tables are required to visualize how exactly input can be changed, or how exactly you can get the desired output when you deal with some of the problems. Okay, now the fifth point is, from the complement table it is easy shown that, so they have gone for that complement thing, x plus x complement equal to 1, or we usually for the explanation we say x plus x dash equal to 1. It is a statement, you have to remember the statement. And while I try to explain the theorem, you are going to get the rough idea how exactly these laws can be used for the solution of the problem. Okay, since 0 plus 0 dash is 0 plus 1 equal to 1, isn't it? So how exactly you got that 0 plus 0 dash? So if x is 0, definitely x complement will be 1, isn't it? I already said x should be written with respect to ulta, isn't it? You have to go for ulta operation, inverse operation. So 0 plus 1 is nothing but 1. So that means if x is 0, if x value is 0, if you go for x plus x dash operation, then you are going to get the output as 1. In the same case 1, if the x value is 1, then how exactly you can see, how exactly you can visualize the concept? It should be like 1 plus 1 dash equal to 1 plus 0 equal to 1. Ultimately you are going to get the value as 1. And in the 5b point you can see x dot x dash equal to 0. So that is nothing but 0 dot 1, because x dash is 1. If the value of x is 0, inverse of 0 is 1. So 0 dot 1 is again 0. So any number multiplied with 0 is ultimately you are going to get the result as 0. So it will verifies the postulate 5. So all these points are required just to verify that whatever the postulates I have listed out in the previous slides, it has to be true, it has to be holds good. So that is the reason why they try to build these tables. Okay, so all these concepts are available in the textbook, but as the soft copy is not available with me, so that is the reason why I have taken the photo and I have tried to explain these things. Okay, now you can see this table will list out all the postulates and theorems. You can see there postulate 2 is required, that is nothing but x plus 0 equal to x. So and x dot 1 equal to x, you have to remember this. Okay, it is better you note down somewhere, so that whatever the problems you get based on that postulates, you can try to solve it. So in the definitely I am pretty sure that in PUC also you would have gone for this Boolean algebra concepts, and you may be having the rough idea of this Boolean algebra concept, okay, postulates and all. So but if you are new to this, I request you to note down this postulate somewhere, so that whenever you try to solve the problems, you can implement these postulates to get the appropriate solution. Fine. So the postulate 5 is x plus x dash equal to 1. In the same case, x dot x dash equal to 0. So you can check the theorem 1. It is nothing but x plus x equal to x, and x dot x equal to again x. Fine. And in theorem 2 you can see x plus 1 equal to 1, and x dot 0 equal to 0. So these are the standard statements which you have to remember. Now in the same case you can see the rest of the laws as well, in say involution law or commutative, associative, distributive, De Morgan's and absorption law. So each and every law will be having its own proof or its own set of proof. You can note it down, and I will explain how exactly you can make use of this law for the theorems. So you can check the theorem 1, how exactly you can solve the theorem 1. X plus x equal to x. Now whenever you get this kind of statement, how exactly you can prove it? You can see in the second line, see x plus x equal to x plus x dot 1. From where you got that? From postulate 2b. From postulate 2b you represented x as x plus x dot 1. Fine. Now how can you deal with 1? So 1 is nothing but x plus x dash, isn't it? You can see the postulate 5. In the above table you can see x plus x dash equal to 1. So what they have gone for? So whenever you get 1, they changed, or they applied postulate 5 in the place of 1. They got x plus x dash. So ultimately what you got? X plus x into x plus x dash. Fine. Now you go for the normal operation, x plus x dash. From where? 4b. So that is the reason why postulates are important. So whatever the postulates I listed out in the previous slide, it is better you you take down somewhere, and so that whenever you have the solution or whenever you have the problem, you can replace the postulate and you can get the, or you can obtain the value, ultimate value. Now when you have x plus x into x dash, so obviously it is a dot operator. X dot x dash is nothing but 0. You can see the postulate 5b. So x dot x dash is 0. So you have to replace that particular place with the 0. Ultimately you are going to get as x plus 0 is nothing but x. Hence the proof. Can you see the theorem 1? Yeah. So that is the reason why how exactly you can prove that x plus x equal to x based on the postulate. Now in the same case, theorem 1b, x dot x equal to x. Again you are going to work in the same fashion. X can be represented as x dot x plus 0, and in the place of 0 what you can do in the place of 0 you can go for x dot x dash. Fine. Once you get x into x plus x into x dash, you are going to make it separately using the postulate 4a, that is nothing but x bracket open x plus x dash. Now x plus x dash is nothing but 1. So 1 into x equal to x. Ultimately you are going to get the value of x. So you are going to get the proof. Fine. Now there is one note that theorem 1b is the dual of theorem 1a, and that each step of the proof in the part b is a dual part of a. So ultimately they are going to say that it is a dual theorem. So that is nothing but x plus x equal to x, as well as x dot x equal to again x. So ultimately they try to prove the theorem by taking the help of postulates. So you can see the theorem 2 or theorem 2a. So x plus 1 equal to 1. Now you have to prove that x plus 1 equal to 1 by taking the appropriate postulates. How can you do that? X plus 1 equal to 1 dot x plus 1. You are going to get this particular statement by taking the postulate 2b. You have to remember what are the postulates. That is the reason why I said whenever you have the chance, take the or screenshot of postulate or note down the postulate somewhere, so that my explanation will be appropriate for you all by looking at the appropriate postulates, and you can visualize that how exactly we got the proof for the theorem. Fine. Now the second step is 1 can be represented as x plus x dash, and in the place of x plus 1 you have to keep as it is. Now once you get two operators or two operands there, x plus x dash and x plus x1, so you are going to get that you have to minimize that by using x plus x dash into 1. How exactly you can do that? By taking the help of 4b, postulate 4b. Once you get x plus x dash into 1, you are going to get the next step as x plus x dash. Why? X dash dot 1 is nothing but x dash. Now by considering 2b, now final step you get 1 by understanding the concept of fifth postulate, that is nothing but x plus x dash is equal to 1. So ultimately you are going to prove the theorem as x plus 1 equal to 1. Now in the previous theorems you have seen, it is a dual theorem, duality. Same case, theorem 2 also deals with the duality, that is nothing but x dot 0 equal to 0. How you can prove it? Again, you can take the same steps like theorem 2a and you can try to prove, and you are going to get the result as 0. So instead of going for again, they have gone for the conclusion that it is with respect to duality. Fine. Now there is one more theorem, theorem 3. So that is nothing but x complement to the complement is x. Now how exactly you can do that? From postulate 5 we know that x plus x dash equal to 1 and x dot x dash equal to 0, which defines the complement of x, isn't it? A complement, how can you deal with the complement of x? The same concept is available. So you can see the solution, x complement to the complement is x. How can you do that? So if the value of x is 0, for example, okay, consider x value is 0. Now what is the complement of 0? It is 1, isn't it? Now again you have to go for the complement. Once if you go for the complement of 1, again you are going to get the value as 0, isn't it? So again 0 is nothing but the value of x. Correct? You have to remember like that. You have to get the solution in that fashion. Okay. Excuse me. The complement of x, complement is x and is also x complement to the complement, isn't it? Double complement. You can see x to the power dash to the power dash, that is nothing but double complements. So whenever you go for double complements, you are going to get the same value. That is the meaning. Therefore, since the complement is unique, we have that x complement to the complement is x. So this is theorem 3. They try to explain this theorem. Okay. Now the theorem is involving 2 or 3 variables may be proven algebraically from the postulates, and the theorems which have already been proven, take for example, so they directly gone for theorem 6a, where x plus xy equal to x. So in the textbook also you can get the same concept. So I did not skip any pages. In the textbook also you are going to see the same concepts. Okay. Now how exactly you can prove theorem 6a? So it is nothing but x plus xy equal to x. Now by considering postulate 2b, you are going to represent x dot 1 plus xy. Okay, x dot 1 plus xy. Fine. Now by considering postulate 4a, how can you minimize that value? It is nothing but x 1 plus y, isn't it? So how exactly you can do that? So if you go for postulate 4a, if you solve it, ultimately you are going to get the value as x dot 1 plus xy, the same thing, isn't it? In the same fashion you have to go for postulate 3a to minimize it again. How exactly you can do that? It is nothing but x y plus 1. You are interchanging the value by considering the postulate 3a. So whenever you have such kind of problems, or if the question is like prove theorem 6a, or prove x plus xy equal to x, you should remember all the postulates. Okay, that is the reason why I said it is better you take down the postulate somewhere. Fine. Now by using the theorem 2a, what you are going to do, you are going to get the value as x dot 1. Fine. Now ultimately x dot 1 is nothing but x by considering the postulate 2b. Even though it is understood that any number or any value into 1 is the same value, you ultimately, while for the solution or to get the solution, you explicitly have to write which postulate you have used to get the solution. You have to remember this. Fine. Now the theorem 6b is nothing but again the duality concept, x in the bracket x plus y equal to x. So they instead of going for trying, they directly gone for duality. I request everyone to solve it manually. So whatever the theorems you have seen in 6a, in the same fashion I request you to solve the theorem 6b by taking some of the appropriate postulates and try to solve it. If you have any doubt, you can contact me, you can put the message, or you can drop the message in WhatsApp. I will manually solve and I will let you know how exactly you can get the actual answer for the theorems. Fine. Now there are some truth table. You can see the truth table when you have two inputs x and y, how exactly you can get the value for xy as well as x plus xy. Fine. So you can see 0 0 is nothing but 0 for xy, for x plus xy is 0. Ultimately you have to replace the variables with respect to 0. Variables are nothing but x and xy. You have to take the variables and you can implement your values to that particular position, and you are going to get the truth table easily. Now the algebraic proofs of the associative law and De Morgan's law theorem are long and will not be shown here. Okay, they have said that the ultimate laws will be very long, so they are going, that is the reason why they are not going to show it here. So by looking at the truth table, you can get the rough idea. So for example, they have given one example here, truth table for first De Morgan's theorem, that is nothing but x plus y complement equal to x complement and y complement. So how exactly you are going to get the values for this particular value place. So ultimately what you have to do, you have to take two inputs, as you have only two variables x and y. You have to take the inputs, it is nothing but 0 0 0 1 1 0 1 1. So first you have to check for x plus y, then you have to complement it, then you have to get the value for x complement, you have to get the value for y complement, ultimately you have to get the value for x complement into y complement. So when you have these inputs, there see, building the truth table is not difficult. Just by replacing the value you can get it. How exactly you got the x complement as 1? I said inverse law, isn't it? You have to go for inversing or not operation. Fine. In the same case, they have gone for rest of the values. You just visualize it, you just try to follow it. If you have any doubt, you can ask me, but there is nothing like a rocket science here. It is a small thing, inversion operation, as well as whatever the theorems they have gone for. Instead of going for the variables, they just implemented their values to that particular variables and they got the output. Okay, now there are some concepts of operator precedence here. See, the operator precedence for evaluating boolean expression is 1. So the parenthesis, whatever the values you put inside the parenthesis, that will be solved first. You have to remember this. The second one is not operation. Inverse law should be solved next, then and then or. So in the same fashion, this precedence will come. Precedents are nothing but, in the general mathematics, you probably remembering the Bodmer's rule. I hope you remember this Bodmer's rule. Bodmer's rule is nothing but the brackets of division, multiplication, addition and subtraction, isn't it? In the same fashion, you try to solve the expressions. Here also you have some precedence, that is nothing but first one is parenthesis, second one is not operation, third one is and fourth one is or. In the same fashion, you have to go for the actual operations and actual solutions. That is the thing they have listed out here. So the last but not the least, you have the concept of Venn diagram. Venn diagram is an illustration that uses circles to show the relationship between the finite groups of things. So in mathematics, in the general maths also, I hope you have gone for Venn diagram concept. The same concepts involved in this subject also, but you have to recall the previous concepts, whatever the concepts you have learned in 10th or 8th or 9th, 10th or PUC. In general mathematics, you have the concept of Venn diagram. The same concepts are applied in this particular subject also. Instead of going for the rest of the things or whatever the special things you see in computer organization, whenever you deal with zeros and ones, when you have finite set of groups, ultimately to represent those steps, you need the Venn diagram concept. Fine, that is the thing. So Venn diagram helps to visually represent the similarities and difference between the two concepts. So that is the reason why you use Venn diagram. So you can see the Venn diagram example here. So they have gone for some theoretical concepts, that is nothing but a helpful illustration that may be used to visualize the relationship among the variables of the Boolean expression is Venn diagram. That is the standard sentence they have gone for. They have given like that. So they have given one example here. You can directly see the figure 2.1 or 2 bar 1, where you have two circles, which first group is of x, second group is of y. Now when you put the operation x bar y bar or x complement y complement, how exactly you are going to get the values? That is nothing but x complement y complement, again x y and x complement y complement. Ultimately you are going to get the illustration, or you are going to get the if you have the two variables, that is 2.1. In 2.2, what you are going to see? The Venn diagram illustration of x equal to xy plus x. So if that is the expression, you have two circles for two variables. You are going to put the value and you are going to shade the intersection part of x and y. That is nothing but the Venn diagram. You are going to get the Venn diagram as it is. Fine. So it is for x equal to xy plus x. So when you multiply xy or two circles or two separate finite set of groups, you are going to get that particular value. Though you don't have any special values here, it's the same concept of Venn diagram. So you can go through the textbook, or you can go through your mathematics concept to understand the Venn diagram. Try to solve some simple problems, whatever you have solved in general mathematics in 10th and 8th. You have to recall all those concepts which are required here also. So don't forget the basic concepts of mathematics to solve the this particular subject, or the solutions for the Boolean algebraic expressions. Now the small thing is here, you can see x in the bracket y plus z can be represented in one fashion, and xy plus xz is represented in separate fashion. Why it is like that? You can see the Venn diagram of xy plus xz. How exactly they have gone for shades? So xy is nothing but intersection of x circle and y circle, and xz is nothing but intersection of x circle and z circle. So that is the reason why for those two intersections they have gone for shades. Fine. In the same fashion for xyz also. So x in the bracket y plus z will be solved first. That is the reason why y plus z will be having the intersection, and they have gone for the shades. And for x, ultimately in the overall they have considered x y z. That is the reason why all the circles will be having the shades. So Venn diagram illustration of the distributive law. So this Venn diagram is for distributive law. Understood? So I request everyone to go through the basic concepts of your Venn diagram and Boolean algebra, whatever the concepts you have learned in mathematics. The same concept will be carry forwarded. I repeat, don't forget the basics. The foundation has to be very strong. Okay, so if I sit for all the concepts in depth, then it will be like a mathematics class itself. So instead of wasting the time, it is better you go for the basics with respect to the mathematics, whatever you have learned in first PUC or second PUC or in SSLC also. I hope you have the concept of algebra. You have to remember the simple concepts, but ultimately it is better you take down the postulates somewhere, so that whenever you get some expressions using the postulates, you can prove the any expressions given in the question. Fine. So this much is enough for today. Let me wind up the video here. So if you have any doubt, you can contact me. Thanks for watching. Thank you so much.